screenshot every single slide?
I did.
Oh my gosh.
I screenshotted, took screenshots and edited every single slide. So as far as we get today is as far as we get today.
Yeah.
And then we stop.
What?
Huh?
Thank you. Okay. It's not my deal. You come when you can.
No, I appreciate it. I really do. That's why I'm in this class.
Collisions. Collisions in one dimension. These are awesome. This is one of my favorite things to teach.
Okay, I feel like you say that every day.
Okay, but this is I like it. Collisions in one dimension. This is something that you can just literally see. You can wrap your mind around it. The math is so good.
Is the math easy?
Yeah, super easy. Okay, so types of collisions. We got 3 different types of collisions. We'll talk about each one separately. It says objects in an isolated system interact with each other in 2 basic ways. Either they can collide, which means they're traveling separately and then they collide, bam. Or they're stuck together and they can explode, which I've never taught. I've actually not taught explosion, so this is a new one for me. In an isolated system, both momentum and total energy are conserved, but the energy can change form from one to another. Okay, so let's talk about different changes in energy during a collision. What are some ways that our energy can change? Sound. Okay, sound takes a lot of energy. What else? Heat, sure. Thermal energy, okay. Potential to kinetic, sure. What's that one more way that energy is lost? Okay, so I'm thinking a couple of years ago for Christmas, one of my students was hand making slingshots. Pretty cool deal. And I was like, I got a brother. He needs a slingshot. So I bought a slingshot for my brother, and what else I bought for him were these little clay BBs, or clay pellets, right? Have you ever played with one of these before? Okay, well, 1, you can kill many a bird with the clay pellet. But 2, with this slingshot, if you pull back and you let it go, the clay pellet, upon impact, does what?
Morphs.
It explodes. It's pretty cool. It goes, poof, poof. So it doesn't do any damage. So if you throw these clay pellets at a picket fence, or we shot our shed a whole lot, then when it rains, they just disappear, and it's fine. And it's biodegradable. It's really nice. That is a total loss of energy in a form of deformation. Right? And it's not even there anymore. That's probably the biggest way that we see things change energy or lose energy is in the form of deformation, meaning it changes shape, right? Think of a car. If it's a tiny little car colliding with something that's pretty substantial, you're going to lose a lot of energy to the crumpling of the car, right? Okay, so it says conservation of momentum and change in kinetic energy can predict what happens in these events. These are 3 different types of collisions, and we want to take note. On an inelastic collision, 2 objects collide, converting some kinetic energy into other forms, such as potential, heat, or sound. On elastic collisions, and this is going to be where the 2 objects bounce. That's how I remember elastic. I think that these are objects that bounce. Objects that bounce. Either they bounce apart or they bounce off of the floor, something like that. 2 objects collide and bounce off each other. You probably want to write these down. Inelastic, they collide. A lot of times they'll stick together. The biggest thing you need to know about elastic collisions is that they conserve kinetic energy. Total kinetic energy is not changed into any other type. Energy is not transformed. On an elastic collision, kinetic energy is conserved. That's huge. Huge concept here. And then explosions is going to be kind of an inelastic collision in reverse. An object that is stuck together breaks apart. A lot of times you'll lose energy to heat, light, sound. Think fireworks. pretty fun display of loss of energy. Oh gosh. It's terrible. Even I know that one's terrible. Yeah.
We never did explosions last year. That sounds fun.
Yeah. Kaboom.
Explosions. We should do a lab.
We should do a lab. How many ways could Arminta get fired? We should do a lab
We do that
about
as well.
explosions.
Cynthia did an explosion in her room, so
We do the egg drop, but we don't put anything.
To be
around the egg.
to be fair, so did mine.
Yeah, they did.
Do an
The egg.
explosion in my room.
Oh yeah.
Oh, that also happened.
We should do the egg drop in your microwave, but we don't put
They
anything around
did.
the eggs, and they just explode when they hit the ground.
Okay, so further discussion here on inelastic collisions.
We can take a picture of it. Or we could do a slingshot with an egg.
Even better. That's
at the board.
At the board.
Slingshot the egg.
Yes.
Gosh.
We slingshot it directly down to add to gravity, and it just like explodes at the ground really fast.
We can also talk about projectile motion.
And then we like see how long it took. It's a
Okay.
concept. It's a good idea.
It's an idea. Is it good?
Is it good? It is an idea though.
No.
Huh. Mm. Okay. Inelastic collisions. So this is going to be breaking down inelastic collisions into two different kinds. One is going to be general inelastic collisions. This is when two objects collide, they bounce off of each other, but you have lost some kinetic energy. Okay, I didn't think this kind existed because I had only taught hypothetical physics or honors physics, algebra-based physics. And in that world, this is not a thing. But in the real world, we do have general inelastic collisions. Two objects collide, they bounce off of each other, move separately after their collision, but there is a loss of kinetic energy. They transfer some of the kinetic energy into other forms. Okay. So this is a type of collision where at the end I have two objects moving separately, but the change in kinetic energy is something. It is a number. There is some kind of loss. And that loss could be due to the things we talked about: sound, heat, deformation.
This, or would they actually?
They would actually be moved apart. Okay, so think of like a bumper car situation. Or bumper cars are kind of not the best example there. Think of just a vehicle accident. If the two cars have collided and one of them's crunched up, but at the end they're not attached, so still two different vehicles, then that would be classified as a general inelastic collision. You could see loss of energy, most of the time due to deformation or sound. Okay, but they're not attached at the end. That's the rule here. Otherwise, on a perfectly inelastic collision, the two objects collide and they stick together as one mass. Okay, collide, stick together as one mass after the collision. Guys, that's the huge part. Perfectly inelastic collision, they stick together. Okay, so now I'm thinking of a car accident or a vehicle accident where the two cars collide and then they're this entangled mass and it moves together as one. Okay, or the clay shots. Again, that's a thought. If those two clay balls were to collide in midair because they're clay, chances are they stick together, and then they move as one. Okay, and the math is going to really represent that well. Are y'all good with this slide?
It's just like one minus the other.
Yeah. Okay, elastic collisions. Now this is different. It says there is really no such thing as a perfect elastic collision. During all collisions, some kinetic energy is transformed into other forms of energy, but some collisions transfer so little energy away from kinetic that they can be dealt with as perfect elastic collisions. Okay, this is the chemistry part of it. It says collisions between molecules are perfect elastic collisions. That's where we get the gas law. M1v1 plus M2v2 equals M1v1 plus M2v2. It's nice.
I don't miss that.
Don't miss that. I don't know anything about it, so I'm just going to move on. Other examples include a steel ball bearing dropping on a steel ball plate, a rubber super ball bouncing on the ground. What we love about those rubber super balls, you know what I'm talking about? Like the super bouncy balls?
They bounce all the way back up.
They bounce all the way back up. Why? Because no energy is lost in the bounce. As hard as I throw it down, it can reverb, right? Because I'm not losing any energy. It's cool. I also think we use billiard balls. Then they say billiard balls. You know what a billiard is?
Yeah.
Pool balls. Okay? If I have two pool balls colliding, chances of them actually sticking together and moving as one, not going to happen. They're going to bounce. And they're going to reverb and have the exact same amount of energy in the final setup as they had in the initial setup. Right? You're not going to see, the only kind of energy I could see losing there would be sound. And it's so negligible that you don't see a whole lot of loss in kinetic energy. Okay? Have you seen the Newton's cradle? Do you know what I'm talking about?
Yeah.
This is kind of that idea where if I have this little ball swinging and I've got three other ones and I drop this first one down, what's this last one going to do?
Gonna go up the same height.
Same height. Same height. Conservation. Okay? That momentum carries all the way through. Click, click, click. And if I pull this one out a little further, what's this one going to do at the end? Go a little further, right? We call that the angle of theta. And it's going to be held all the way through. Cool? Okay. I had a comic that I showed to my honors physics class. It's like a physics teacher on a playground, and he's got all of his little students set up on the swing set. He's got one pulled out here.
I remember that.
That's why we don't do playground duty. Explosions act the other way. Explosions are kind of perfectly inelastic collisions. So imagine these objects are separate, and then they collide, and they stick together, and they move as one. Explosions are that backwards. You start out with this one object, and then it explodes, and then you have separately moving pieces afterwards. Okay, so it's like running an inelastic collision in reverse. Okay, let's do math. We'll talk more about this later. I do think this slide is very handy for you. In your text, in your slides that you have access to, this is slide 45. Slide 45. You're going to want to write that down. This table is super handy. Okay. And if you don't write down anything else, you don't want to take notes on this particular table, what you should see here in this column is that momentum is always conserved. Write that down. Momentum is always conserved. This is going to be a type of question that they'll ask you. Momentum is always conserved. I would put always in all caps. Momentum is always conserved. But kinetic energy is conserved only in perfect elastic collisions or inelastic collisions. Kinetic energy is conserved only in elastic collisions. So what you would see there is the change in kinetic energy equals 0. No joules lost or gained. Kinetic energy is only conserved in elastic collisions. Momentum is always conserved. Kinetic energy is only conserved in elastic collisions. Go fight win. Ready to go on? Lily Marie, are you ready? Okay. All right, so this is example or question 16. In the absence of an external force, momentum is conserved in which of the following collisions? All of them. Okay, momentum is always conserved. So again, Make sure you have that on paper. You may want to write it again. You need to know that. Okay? Guaranteed 2 or 3 questions asking that same thing. All right. Second question, 17. It says, in the absence of an external force, kinetic energy is conserved in which of the following types?
Elastic.
Only elastic. Only elastic. Why?
Because all the other ones lose energy to other things.
Okay, but what's typical of an elastic collision?
Bounce.
They bounce. It bounces. And it bounces with the same amount of energy that it had in the beginning. Okay. Conservation of momentum. Okay, so how do we handle that momentum is conserved? It says during a collision or an explosion, measurements show that the total momentum of a closed system does not change. Momentum is held. The diagram shows how that works. In my honors physics class, we say M1 V1 naught plus M2 V2 F. Naught, sorry. Equals M1 V1 F. Here they're using the prime tick marks to show that this is final. Okay. So how would you talk about the equal sign? What do you think that moment is? That's the point of impact. Okay, so this stuff on the left-hand side would be your stuff before they collide. Your equal sign is the moment of impact. Your stuff on the right side is everything that happens after the collision. Okay, so those prime marks, I think they're a little bit more user-friendly than the Fs. But that's what they imply. They imply that this is post-collision and pre-collision. And your equal sign is the moment that they collide. Any questions on that? Should you write the formula? Sure. Remember that MV means what? Mass times velocity. What is that? MV.
It's the integral force.
Okay. What does it measure?
Power.
No?
No.
Somebody read the title of this slide.
Oh.
Momentum.
Momentum.
MV is momentum. MV is momentum. Do you remember what letter we usually use for this?
P.
Right, the rho.
Or the rho. That's why I thought it was
Rho.
It's like,
Okay. Yeah. It's a P. J for Jimples. Rho for momentum. I can't make it better. I don't know. I'd like to meet Jimples one day. Okay, so perfectly inelastic collisions. This is when the two objects collide, they stick together, they move as one afterwards. Look at this beautiful formula. Doesn't that make your heart happy?
Yeah.
Because on the other one, look, I have two separate objects initially, and I have two separate objects finally. They collide, they bounce, they do their thing. Here, they collide and they stick together.
So they're moving.
So we have a combined mass, ma plus mb, moving at one velocity, vf. It's beautiful. You should write this one down. You're going to need this one. This is for a perfect inelastic collision. They move together. They fit together. We add up the mass of the new unified object. And they have only one final velocity. Right here. I love it when the math tells the story. I think that's what you see here. That's why I got so excited about the potential energy curves, because I could imagine dropping a marble into that roller coaster. It seemed pretty cool to me. So V is a vector, so it's got an arrow on top, and then out to the side, it's got a prime mark, which tells you this is the final velocity. Good question. Ready? All right, so here's some problems we get to work. 13,500 kilogram railroad freight car travels on a level track at a speed of 4.5 meters per second. It collides and couples. This is how you know it's inelastic. They stick together. It collides and couples with a 25 kilogram second car initially at rest. Okay, so if you're riding M1V1, you're going to have 13,500. This is mass 1, and its initial velocity is 4.5 meters per second. Plus M2V2 is going to be 25,000. And that object, the second car, is initially at rest. Equal to their entangled mass, 13,500 plus 25,000, times their final velocity VF. And the question is, what's the speed of the two freight cars after the collision? So this second half is going to cancel out. And you're going to divide 13,500 times 4.5 by their combined mass, 13,500 plus 25,000. And that's going to equal the system's final velocity, their final velocity. Remember that this final velocity is a vector quantity. Okay. If the first object is moving to the right and it hits the second one that's sitting still, it feels like they will continue moving to the right. What's our answer here? C? Okay. I hid the answers, so I can't pop them up anymore. These are screenshots, not active slides. Did we all get C, though? Okay. Not that I don't trust you, Seth. We're going to double check. Trust but verify. That's what our calculus book said one day, right? All right, cannonball with a mass of 100 kilograms flies in the horizontal direction with a speed of 250 meters per second. I thought this was just a ball when I first worked this problem. I didn't realize it was a cannonball. And so I really didn't understand the impact that this ball would have on a ship. Reading it again, though, it makes a whole lot more sense. Okay, so cannonball, mass of 100, flies in the horizontal direction with a speed of 250 meters per second. And then it strikes the ship, which is initially at rest, so you're going to have the same setup. The mass of the ship is 15,000. Find the speed of the ship after the ball becomes embedded in it. Again, that verb embedded, that tells me this is inelastic. Okay, 1.7. Any questions on this, y'all?
What about ones that bounce?
What about ones that bounce? We'll work some of those later. We're not going to talk about those yet. One thing that I want you to think about, it's really easy to imagine this kind of setup where the ball becomes part of the ship. A problem that I have seen before is a kid running and jumping on his skateboard. That's an inelastic collision. Why? Because he was one mass, the skateboard was separate, we went and ran and jumped on it, now they're together. Okay, so that's a type of inelastic collision. I have seen, this would be more of an example of an explosion, but they said that there was like a spaceman in outer space and he's untethered from his rocket ship, right? And so he just starts chunking objects to get back to where he's supposed to be. This would be a type of explosion because his best move to gain momentum in the opposite direction is to throw things this way. And imagine he's in a vacuum, right? And so everything that he has has an equal and opposite reaction. So he starts exploding his pieces of equipment. He throws his air tank. He throws his wrench. He doesn't last long after he threw his air tank. You understand, like, this idea of this, it's not always just a bam collision. I also have seen a problem where a man's running on a dock and he jumps into his boat. Got a man in a boat now. That's a collided object. Cool? Okay, so it's not always huge collision type thing. Anytime two objects are moving and now they're moving as one, that's an inelastic collision. Okay. Last one. A 40 kilogram girl skates on at 5.5 meters per second on ice toward her 70 kilogram friend who is standing still with arms open. Isn't that just such a sweet problem? Gag. As they collide and hold each other, what is their speed after the collision?
2.
And I wonder if they don't rotate. You know what I mean?
Yeah, like they just like fall to the ground.
I wonder. Her friend is standing still with arms open. It feels like, though, on an ice skating rink on a frictionless surface, there might be some kind of angular something that happens after they collide. I imagine that they don't move in a linear direction. I don't know. Maybe they would. Depends. Anybody got a number here?
2.
2. Pick 2. Pick 2. All good?